Alrighty, welcome back. This is part 2 of the properties functions function vocabulary videos. Last video ended talking about local and absolute extrema. So we have in front of us on the screen the information that we filled out last time about local and absolute extrema, and we know that extrema also is another way of saying minimum or minima and maxima, so the plural of minimum and maximum. And we looked at a graph, and we looked at where the local max and the absolute max are. We found the local or relative min, and we noticed that there is no absolute minimum. There is an absolute maximum, but there is no absolute minimum. We can see that, and I'll highlight it in red. We see it because the graph continues down to negative infinity in both directions. There's a little bit of information here on the side about finding local extrema on your calculator. What I'd like to do is to have you go through that, follow these directions, find the local max, the local min, the absolute max, absolute min, if they exist, and we'll go over them in class, next class. Alright, so the next thing that we're going to talk about is symmetry. Symmetry is talking about a sort of balance that we have in our graphs. And so the first type of symmetry that we're going to talk about is symmetry with respect to the x-axis. Graph that has symmetry with respect to the x-axis is symmetric or reflected over the x-axis. Graphically, we know that this is our x-axis right here. So whatever we're going to draw above the x-axis, we'll have the mirror image below the x-axis. For example, if I go up here, let's see how well I can draw this. The mirror image will come down below. Been close enough. And you can see that every point here, let's call point here x, y, that there will be a mirrored point, which is x comma negative y. That's for every single point along here. It doesn't matter which point you choose. Just change the y from positive to negative or negative to positive, and you'll get another point on the graph. So if I were to numerically or tabularly look at this, we could say, let's say that's negative 3, negative 2, negative 1, 0, 1. So at negative 3 it's 0. Let's say at negative 2 it's, well, it would be positive and negative 1. There would be two values, up and down, a positive value and a negative value. At negative 1, let's say that is plus or minus 2. At 0, let's say plus or minus 2.5, and a 1 plus or minus 2.75. I am totally making these up, but the key here are the plus and minus values. We see that each x value has two function values. So what we see here is that these are not functions. They fail the vertical line test, VLT. But what we can say about it, and I said this already, is that if x and y is on the graph, we know that x comma negative y is on the graph. For example, if I know 1 comma 2 is on the graph, then I know that 1 comma negative 2 is on the graph. Or if I know that, say, 3 comma negative 5 is on the graph, then I know that 3 comma 5 is also on the graph. So it goes both ways. Alright, so the next type of symmetry we're going to talk about is going to be symmetry with respect to the y-axis. So again, this is symmetric or reflected over the y axis. Again, graphically, I'm going to find my y-axis, and I know that it's going to be a mirror image over this y-axis. So I could do something like this. This, pretty good drawing, is a graph of a function that is symmetric over the y-axis. It's a mirror. So for every point x comma y, I know that I'm going to have negative x comma y is going to be another point. Looking at the table, x and f of x, I could do -3, -2, -1, 0, 1, 2. Let's say this starts at 1, 0, -1, -2, 1, 0. You'll notice that there are pairs here. The -2, 0 and the 2, 0 are together. We have our -1, that shouldn't be negative. This should, oh, there's a mistake. This should be negative. Okay? So the f of x value should be the same, but the x value changes. So algebraically, we say for all x values in the domain, we know that f of x is going to be equal to f of negative x. Another way of saying that is that if I have a point x, y, I know that there must also be a negative x, y point. -3 comma 1 tells me I'm also going to have 3 comma 1 in there. We have another name for them. They're called even functions. These are functions. They're called even functions because functions in the form x to the n, where n is even, are all symmetric to the y-axis. Let me just circle this in a slightly different color. Talk about another name, another vocab term that we'll be using. Alrighty. Now the last one is symmetry with respect to the origin. Again, we're going to have something that is symmetric or reflected over the origin. That's kind of strange because now we have a mirror image or a reflection over a point. That's difficult to do. How do we do that? Well, we have our point here, that's our origin, which means any point I have, any x, y, will also have, if I reflect it directly over, same distance, we'll have a negative x, negative y. So here I have a function like this. Algebraically, let's say -3, -8, -2, -4, -1, -1, 0, 0, 1, 1, 2, 4, 3, 8. Running out of room here, but you can see that there's a pattern. And algebraically, for all x values in the domain, we notice something about our function values. We know that f of negative x is actually equal to negative f of x. How do I see that? Well, -8, -3 changes to 3 comma 8, or if I have an x and y, that's going to relate to a negative x, negative y. I can flip both the x and the y and get the same value. We have a special name for this. We call them odd functions, because functions f of x equals x to the n when n is odd, again, are going to have origin symmetry. Alright, so that's our symmetry lesson. The last thing we're going to talk about is asymptotes, and kind of more importantly, limit notation. And we'll be coming back to this idea of limit notation later. It becomes very important when we get on into calculus. Alright, so vertical asymptote. We'll start with that. So a vertical asymptote is a vertical line. So for example, x equals a. And the graph, as it approaches that line, that value, x equals a, is going to increase or decrease without bound. What does it mean to increase or decrease without bound? Well, it means that my f of x is going to go to positive or negative infinity. Increase means positive, decrease means negative. So as x approaches some number, it's going to shoot off in both directions, up and down, or both up, both down, one of each. In limit notation, now this is we start talking about really cool, nifty looking stuff. We describe this behavior of x and f of x in relationship to each other. So if, oh, that's a typo, that shouldn't say x, y, it should be x equals a, is a vertical asymptote. We have a vertical asymptote, then we would write that the limit as x approaches a, now the x arrow a is a little bit smaller, and then we write f of x big right next to it. Well, what happens to f of x? When you're talking about a vertical asymptote, it's going off in both directions. So it's either going to, and we see it up top, we see that up top up there. Let me erase that. That's going to be strange if I leave that. But that it approaches positive or negative infinity. It never crosses. We never ever cross the line x equals a. Horizontal asymptotes are very similar, but it's a horizontal line, so we'll call it y equals b. And it's the graph that the function approaches at the ends of the graph as x approaches infinity or negative infinity. I can say positive infinity or negative infinity. So as we go off to positive infinity or to negative infinity, what does our graph approach? What number, what value does it approach? So again, dealing with limit notation, we can write this as the limit, we write lim for that, as x approaches positive or negative infinity, f of x is going to get closer and closer to some value, we'll call it b. So what I'll do here is I will draw quickly what we can see in with a vertical asymptote and a horizontal asymptote. So if I have my value a here, my graph, if I draw a dotted line for that vertical asymptote, that's x equals some value, my graph will shoot off, will approach but never cross that line. So this dotted, dashed line, however you want to call it, is sort of a no-fly zone. Nothing can go there. For a horizontal asymptote, say y equals b. Could be some value, could be 0, could be positive, could be negative. We'll just call it b. And what will happen is, at the ends, the graph will approach it, either from above and below, or both from below. So here is a type of graph that actually approaches. It's a very poor drawing, it's not supposed to cross here, but it's a really big point there. This is a graph that you might run into that approaches both from above and below. I've run out of time, unfortunately. We still need to talk about end behavior. So I will have a part 3 for you, just dealing with right and left hand behavior and limit notation, talking about that. So come back next, part 3, to view about end behavior and to finish up section 1.2. Alright, see you soon.